There are three particles that make up an atom. They are protons, electrons, and neutrons. I'm trying to write a little faster. Now these particles are very, very small. They carry a charge. A proton is a positive charge, an electron is a negative charge, and a neutron is considered to have a neutral charge. The mass associated with each particle, a proton, is considered to have the mass of one atomic mass unit. Atomic mass, mu. Okay. Neutron has the same mass, one atomic mass unit. And the mass of an electron is 1/1810th atomic mass units. Now the atomic mass unit is a theoretical amount because it's far too small for anybody to ever come up with a way to mass that directly. But as we'll see later on in this course, if you happen to take one atomic mass unit and multiply it by 1 AMU and multiply it by Avogadro's number, so times 6.02 times 10 to the 23rd, you end up equaling 1 gram. It's going to be a big deal. We're going to use this relationship a lot. Anyway, I didn't write that correctly. I better fix that. Oh, brother. Oops. Times 10. I gotta get the 10 to the 23rd. Equals 1 gram. But we'll come back to that later. So I have these three subatomic particles: protons, electrons, and neutrons. Neutrons, I want you to start thinking of a neutron as the atomic glue that holds protons together in the nucleus. Protons are positively charged, okay? And if you're trying to put a whole bunch of positively charged particles together, they would normally repel each other. But because there are neutrons holding them together, they can all reside comfortably in the nucleus. The electrons are going to be outside the nucleus, and we'll talk about where they're going to be a little later. Right now, okay, protons, neutrons, in the middle, the nucleus, the electrons surrounding the nucleus. Protons positive, electrons negative. So I want to talk about a symbol on the periodic table, and I'll pick phosphorus, okay? So if you look up on the periodic table, you're going to see P. You're going to see phosphorus, okay? And it'll have the number 15 by it, and it's also going to have the number 30.97376. 97376, all right? Now this number right here, we call that the atomic number. And what the atomic number stands for is the number of protons, atomic number. It turns out that the protons, the number of protons, are what give an element its properties. So if you change the atomic number, you're going to have a different element, obviously, and the atomic number is equal to the number of protons. So looking at this symbol, what identifies phosphorus as phosphorus is the fact that it has 15 protons. I change the number of protons, I change the element. So, okay, number of protons. Now this number right here, this has a couple different names, actually more than that, but the two most common names are mass number or, get that written, oops, kind of weird B, mass number or atomic mass. And what the atomic mass or mass number is equal to is the sum of those particles which make up most of the mass of an atom. So that would be the protons and the neutrons. Okay? So protons and neutrons, when added together, are going to equal the atomic mass. So that's equal to protons plus neutrons. Now sometimes, quite often actually, an element, neutrons, oops, what the heck, get rid of that, get back to this, what the heck, not sure what to do. Whatever I did, we'll figure that out. Where was I? Oh yeah, I was talking about sometimes there's going to be a different number of neutrons holding the protons of an element together in the nucleus, in which case you get what's called an isotope. Okay? So an isotope has a different number of neutrons. Okay? So, as it turns out, when you look at this number, that is what is said to be the weighted average of all the different isotopes that are present in nature of a certain element. So that's the atomic average atomic masses of the isotopes. Okay, that's right there. So that's why that number is a fractional number, because if you think about it and you look up here and you go, okay, protons are one atomic mass unit, neutrons are another atomic mass, one whole atomic mass unit, and then I make the statement down here that protons and neutrons equal the atomic mass. How can I get this number of, you know, multiple little digits, you know, decimals, 0.973. Where's this 0.9, this stuff coming from right here? Well, then you might think, okay, maybe it's the electrons. Well, the electrons aren't included in that. Where this number comes from is that it is the average of the atomic isotopes that are present in nature. So you can figure out what the atomic mass is based on the number of isotopes present. For example, if I'm looking at an element, the element bromine, okay? And I find out that 50.92% of the bromine atoms that I test, okay, from a sample of bromine naturally occurring, are going to have an atomic number of 79 atomic mass units. Oops, not ATMs, that's atmospheres. We talk about those later. Atomic mass units. Well, that leaves, in the case of bromine, that 43 or 49.31% has the atomic mass of 81. Okay? Now some elements have more isotopes than that. Okay? Some of them just have a whole lot more isotopes than that. But bromine has these. How do I figure out what bromine's atomic number is, weighted? Well, I use this formula that's going to look like this. Atomic mass, which is what we're looking for. Okay. Oops. Oops. Messed everything up on that one. Atomic. Get the idea. Mass down here. Got to write kind of slow. Is equal to, it'll be the percentage found, 0.5092 times that isotope's mass, 91 AMU. All right? Plus the second isotope. Well, 49.31% of that, okay, has the atomic mass of 81 AMU. Now, if there were more isotopes, if a problem gave you more isotopes, you just add those onto the end. Plus, oops, blump, 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 keep going, keep going, keep going. But since you're only given 2 isotopes of bromine, I can solve this. So what I'm going to do, okay, take the calculator. I'm going to sit there and go 0.5092 times 79. That quantity is going to be, make it green, 40.22. Then I'm going to add to that, okay, 0.4931 times 81. I'm going to get 39.94. Okay, that means that my answer is, for the atomic mass, 80.16 or thereabouts. Okay, so this would have been 80.16 right there. So that's how you calculate the average atomic mass of an element. All right.